In this video we will cover generators and how they help us save memory. During our journey so far we've actually used one kind of generator very often, and that was range. Range generated us numbers. So for example, we could iterate through these numbers by writing for I in range 10. And now the special thing with range is that the numbers 0 to 9 are not generated all at once. So this is not the same as having a list from the numbers 0 to 10 here. Because range will only generate the numbers when they're actually needed. So we could write here 100,000 or even 100 million, and this would not affect our memory because the actual numbers are only generated for each respective for loop step. And this concept of generating or evaluating things only when we need them is called lazy evaluation. And so far we've only seen the generating part, but this also works for evaluation. So we can imagine that we have a function called square that takes some list of numbers and then returns maybe as a list comprehension the square of the values. So you write element squared for element in A. And this computes the square of every element and then returns the whole list. And of course, for just 3 numbers, this is not a problem, but if we're dealing with huge datasets, then it can be problematic if we have to load the whole dataset into our memory when we do some computation. In this example, currently, of course, the whole list is required since we want to print it, but if we now have a for loop, then we actually don't require all the elements for every step. So it would be enough to first calculate the square of the first element, and then for the second for loop step, the second square, and so on. Note that the computation time is not affected. So eventually, if we run through the whole for loop, every number will be squared, regardless of whether we use a generator or list comprehension in this case. Okay, so how do we turn this into a generator? The first thing we write is a for loop. So for element in A. And now the important thing is that we don't loop through this whole list and then return the results, but instead we yield a result for every element. So we square the element and that is then yielded. And so if we run that, we get the same output, but what happens internally, and we can also check that. So if we print square, it will first tell us it's a normal function. And if we then actually call it with some random list, then it tells us it's a generator object. And so with this syntax here, we then loop through this generator, which yields us one squared element at a time. So maybe let's make it a bit more readable. We have a generator for squaring, and that is initialized by calling the square function with some list. And then we can loop through this generator, which will evaluate or compute the square for each element at a time, and then yield us the result, which we print in here. Okay, small intermission to clarify how the yield statement works. So here we're not making use of a for loop. And so what happens is that we initialize the generator and then loop through that. And so in the first for loop step, we start at the beginning of the generator until we have the yield 1. So this will be the first element that is yielded or returned. And then we can do something to this element in our code here. So here we print it. And normally when we write functions with return statements, the function ends after returning something. But for the generators, this is not the case. So we yielded the 1, and now this generator is kind of on pause until we want to take the next element from it. So we finish doing whatever we want with our first element, and then we go into the second for loop step. So we're back in our generator, and now we're at this point where the generator yields 2. And then we do something to this 2, and then we go into the last step where the generator yields 3. Okay, now back to our previous code. There's also a shorter syntax for all that. And this syntax is very close to list comprehension. So the normal list comprehension we already had up here. And let's define our A in here. So we calculate the square for every element in our list. We can save this in some other variable, and then we could iterate through that. So this gives us the same result. But of course here we have to calculate all the elements and store them in memory. But now with a very simple change, we can turn this list comprehension into a generator expression. And this is done by simply exchanging the outer square brackets with normal brackets. And now we have a generator which is equivalent to this here. So it will yield us the square of the elements here one step at a time. Of course the output doesn't change, but now our code is more memory friendly.